All right, so the next thing we want to talk about is about polarization. And we know that when you have electromagnetic wave that's being produced, it can propagate along space. It's going to change with time, and so you have the electric field that's that's oscillating up and down. That's one direction. If you know the electric field, oscillating that, and the magnetic field is oscillating in and out of the page, then you will have the propagation directions of wave that is rightward. Okay, so when we do this, most of the time, when you have the electromagnetic wave that's being generated, it can oscillate. Your electric field can oscillate in various directions. Okay, and once you know the directions of the electric field, once you know the propagation direction, then of course the oscillation directions of magnetic field can also be determined. Okay, so generally speaking, when you have electromagnetic wave that's being generated, electric field can oscillate in different directions. And this kind of different direction, we call that light is unpolarized. So now let's going to focus on light, which is the visible spectrum, of the electromagnetic waves. So when you have light, that's what we call unpolarized. We usually use this symbol to indicate that it is unpolarized light. Okay, so in other words, unpolarized light, we use this symbol. So that electric field indicating that electric field can oscillating in various directions. Okay, so what we're going to talk about a very interesting thing is that when you have unpolarized light, and when you send a light through through space or through different methods, that light can be polarized. What does that mean when light can be polarized? When light can be polarized, it means that electric field oscillation will only be in one direction. Okay, so in other words, when the unpolarized light is being sent through a polarizer or through some other method, that light electric field can only oscillate in one direction. And when it does that, we call that light is being polarized. Okay, so you can see that this diagram shows you that when you have an unpolarized light that is sent through a polarizer, and then the only directions of electric field that will remain will be in the same directions as the what we call the polarizing axis. You can see that the vertical line here indicate the polarizing axis. Okay, so you can see that if you have intensity that's called I naught, and when it's sent through this polarizer, half of the electric field will be absorbed by this polarizing sheet, and only half of the light will remain. And that is this direction, and that's in the same direction as the polarizing axis. Okay, so your intensity will by default change by 1/2, because only half of them will remain, will be permitted, and half of them will be absorbed by this device. Okay, and we use that's why. So you can see that intensity is decreased, and that's why on a sunny day, or on a sunny day, we usually wear a sunglasses, because sunglasses is made of polarizing material. So when light passing through the glasses, half of the intensity will be will be absorbed, and half of it will transmit it passing through the glasses. And so that the intensity, so what you see is dimmer, as because intensity is decreased by half. So this is when you have an unpolarized light sent through a polarizer. Half of intensity is being reduced. What about if you put another polarizer in front of the polarized light? What's going to happen? You'll find out the light intensity is going to be further reduced, but by follow the what we call the Malus law. So let me do this. Okay. So this just basically tells you, just explain that the intensity after when it's already been polarized. Let's say, the light is already being polarized, and then you're going to send, let's say the light is being polarized, and then you're going to send it through a second polarizer, and the polarizing axis now is in this direction. If that's in this direction, then we know that light, then again, the polarized light is in this direction. Once it passes through the second polarizer, the only oscillation of electric field that will remain will be the electric field that oscillate in the same direction as the second polarizer. Okay, so that's basically that's basically what the polarizing axis does. It reduces the intensity, and the intensity follows the for the polarized light, it follows the Malus law, which is this. So you have the intensity. Let's say if I, instead of using I naught, let's say this has I naught. After you pass through the and then I'm going to call that I1, which is the when the intensity after you pass through the first polarizer, then it will be 1/2 I naught. Okay, and the intensity after you pass through the second polarizer, I'm going to call that I2. So my I2 is whatever I1 is, and then times cosine theta squared. And that theta, what is that theta? Theta is the the oscillation directions of the incoming light with respect to the polarizing axis. So in this case, because this is vertical, so that's vertical, and this is the polarizing axis of the second polarizer, and the angle here is theta. Okay, so this is so the intensity will be like this. So it's I2 that's equal to I1 cosine theta squared. And what does that tell you? It means that when you put a two polarizer, one against each other, the intensity actually changes depending on the how these two axes are related to each other. Okay, so when theta is equal to 0, meaning that this second polarizer and the first polarizer, they are in the same direction, you'll find that your intensity will remain the same. All the light will pass through. But when theta is 90 degrees, meaning that this one is that, for example, this one's vertical and the other one is horizontal, then, by this equation, we know that there's no intensity. So you will see complete darkness because no light will be permitted. And if you have 45 degrees, of course, then just plug in the 45 and you can calculate the intensity. Okay, so that's basically tells you that when you have two polarized placed in front of each other, you can adjust the relative angle. You can adjust the angle between the two polarizing axes, and then you will see that the light intensity will change as a function of theta. Okay, and you can you can have a situations that all the light will pass through. You can have a situation that all the light will be blocked out, depending on the angle between those two polarizing axes. So that's that is the the property of light when it passes through the polarizer. So initially for the unpolarized, it can be polarized depending on the polarizer. Okay. So now we're going to talk about how what kind of how light is being reflected and refracted. So when we look at this diagram, okay, so this diagram, several things that we need to mention first. So that's the white space indicate air, okay, and then the green indicate let's say a glass, okay. So you have you have an air, you have a glass, which means that, and then this horizontal line we call that interface. So this is the interface of two different material. One is air and one is glass. Okay, and we draw the vertical dash line here. The vertical dash line we call that normal, and it is basically a reference line. So we can imagine that you have an electromagnetic wave that is propagated through space and is striking the surface of the glass. So this light ray is striking at this point. So we call this theta 1, which is in reference to the normal. We call that the angle of incidence. Okay, so this is the angle of incidence, and we found that reflected ray will actually be at the angle that's exactly the same as your theta 1. They are symmetrical about the normal. So this is what we call the reflected ray. So we found that your theta 1 and theta 1 prime are equal to each other. And so this is called the law of reflection. So reflected ray lies in the plane of incident and has the angle of reflection equal to the angle of incidence. Okay, so this is light ray can be reflected off the surface. Okay, And so the angle follows that, these two angles are equal to each other. We also found that light ray can be, can propagate through a second material, but then the angle will not be the same as the angle of incidence. It actually follows the Snell's law, which is called the law of refraction. So when light ray passing through a second different material, light will be refracted. How much is being refracted is determined by the index of refraction. So what is the index of refraction? It is a ratio of speed of light. Okay, so C is the speed of light in air or in vacuum, and V is the speed of light in a different material. So, let's say the velocity, the V here indicate a speed of light in glass. And so when you calculate the ratio, that gives you the index of refraction. So we can see that, your V is always equal or less than C. So your N1 will either, the smallest value of N1 that we know is 1, okay, if it's air or vacuum. And if it's other than air or vacuum, in other words, your V is actually, it will travel slower. So this ratio will be greater. So for glass, you can have a 1 point, I don't know, probably 1.43 or something. Okay, and for diamond, you will have like 2 point something. For water, as 1.33. So the index of refraction can be found, in the textbook. Okay, so when you take the quiz or when you take the exam, you will go go look up the value used in the textbook and use that value, or I will provide those to you. So it follows so when you have a light ray that's being refracted, it follows the law of refraction. So refracted ray lies in the plane of incidence, and the angle incident and the angle refraction is related by this. So you have the N2. So let's say this is N2 and this is N1. So you have the N1 times sine of theta 1, the angle incidence, and that's equal to N2 times sine of theta 2. Okay, again, in reference to the normal. Okay, so you have N2 sine theta 2, that's equal to N1 sine theta 1. So you can see that, depending on the index of refraction, the degree where the refracted ray will be really depends on the index of refraction. Okay, so here's, here are the, some example that say if N1 and N2 are equal to each other, if they're equal to each other, meaning that, they have the same, same index of refraction, then you will find that the incident wave will continue without any deviation, because by Snell's law, N1 sine theta 1, that's equal to N2 sine theta 2, your theta 1 and theta 2 has to be equal to each other when N2 is equal to N1. Okay, what about when N2, this is this is the this has a higher index of refraction and this has a lower index of refraction. If that's the case, then we found that your theta 2 has to be less than theta 1. Again, by applying N1 sine theta 1, that's equal to N2 sine theta 2. When N2 is greater, theta 2 has to be smaller, just so that N1 sine theta 1 is equal to N2 sine theta 2. Meaning that when you have a light ray that's from a lower index of refraction to a higher index to a material that has a higher index of refraction, the refracted ray will be bent toward the normal. Okay. What about the situation is reversed? You have a light ray that's coming from the higher index of refraction to a material that has a lower index of refraction. What we found is that N1 sine theta 1 has to be equal to N2 sine theta 2, because N2 is smaller, meaning that your theta 2 has to be larger. If theta 2 has to be larger, meaning that it's actually bent away from the normal. Okay, so theta 2 has to be greater than theta 1. Okay, and the other phenomena that that you sometimes see is that when you have a light ray, that's white light, that's that's striking on the surface, and we found that in the refracted ray, it actually you will see that different colors of light will actually be be seen instead of one single light ray. You actually see a ray, different rays. You actually see rays of different color, and this is what we call dispersion. Because we know that when you have a light ray that is white, actually consists of light ray of different wavelength. And so when you have a light ray that consists of different wavelengths combined, then that you'll see white color. But when the white ray sent through a device, and it undergo refraction, light will be refracted, and because wavelength is a function of the index of refraction. So for different wavelength, then light ray will be dispersed, meaning that they will be refracted at different angle. So you'll be able to see different colors. Okay. And so this basically says that you have white light that's in a low index material that has a low index of refraction, and coming to refracting into a material that has a high index of refraction. We find that the blue color is actually toward the normal, and the red is away from the normal, meaning that blue actually has the wavelength has a higher index of refraction. And then if the situation is reversed, you have the white light that is coming from the higher index of refraction, and then going to a material that has a lower index of refraction. We found that the red actually will be closer to normal, and the blue will actually be refractive for greater, just so that n1 sine theta 1 is equal to n2 sine theta 2. So the blue light ray will have a larger angle. So this phenomena we call that dispersion. And so you will see that when you have a white light sent through a prism, and you will see that the light the color emerge from the other surface of the prism will actually have a rainbow of of light ray. That's because through double refraction, then the angle of separation between the different colors of light will be greater, so you can actually easily see like blue, red, red, blue, and things like that. Okay. And so another interesting phenomena, and a lot that we use a lot application, is what we call a total internal reflection. So what is total internal reflection? We actually use that a lot in the applications of cable, okay, or fiber optics. If you have if you've seen the fiber optics, you'll see that light propagated within that device. You don't see light emanating from that device, and that's the applications of fiber optics or cable, and utilize the concept of total internal reflection. So total internal reflection will only occur when the light source is in a material that has a higher index of refraction. Okay, so let's look at this diagram. So you have the light source that's in the higher index of refraction. So you have one light ray that is shined on the interface perpendicularly, because it's perpendicularly, so there's no deviation. And then you have another light ray that's striking the surface at this angle. So this is normal. So this is the angle of incidence, and this is angle of refraction. So light will be refracted, and you can have a larger index, larger angle of incidence, and you'll find that you have a even greater angle of refraction, because and then larger and larger until and you can see that the light, the refracted light in the air is actually get bent, has a larger angle refraction until when you hit an angle, when the angle of incidence is what we call the critical angle, then you find that the refracted ray is actually propagating along the interface. Okay, so when the refracted ray is propagating along the interface, we call that the angle of incidence is the critical angle. So how do we find the critical angle? You'll find that N1, so this is your N1. So you have N1 sine theta C that's equal to N2 sine 90 degrees, because the angle of refraction is 90. So in that case, your critical angle can be found by using this, which is the inverse sine of N2 over N1. N2 is the N2 has a lower index of refraction, N1 has a higher index of refraction. So in other words, when your angle of incidence is equal to the critical angle, then all the refracted ray will propagating along the interface. Now imagine that if you have a larger angle that's greater than the critical angle, what's going to happen? What's going to happen is that because the refracted ray will, when theta, or angle of incidence, is equal to the critical angle, refracted ray propagating along the interface. When this angle is greater than critical angle, what we found is that light will not be seen on the in the second material. Instead, it will actually be reflected back into itself. Okay, so this is what we call a total internal reflection. Any angle that's greater than the critical angle, you'll find that all the light ray will be reflected back into itself, meaning that your light ray will be trapped within this device. No light ray will be outside this device. Okay, so this is how we how we use this in the fiber optics, because as long as the angle of incidence is greater than the critical angle, all the light ray will be trapped inside this device. No light ray will be outside the device. Okay, so so that's basically the applications of the total internal reflection for information transmission, or for electricity transmission, or even for fiber optics that we use in the cable, that they just so that you don't, so all the energy will propagate within this this device, so that it can being transported long distance. Okay, all right, so that's what we call the total internal reflection. And there's another one that's also very interesting. Let me see. And this is what we call the let me erase this. And that is what we call the polarization by reflection. We earlier we mentioned that light can be polarized, either sent through a polarizing sheet, or by some other methods. And this is what one of the other method, that is by reflection. So polarization can be caused by reflection. So let's see how it works. So imagine that you have air, you have a glass. So this is the interface. You have the normal, and we have a light ray that is being shine on, that's propagating and shine on the interface. Okay, so initially this light ray is unpolarized, and we use the this arrow to indicate the propagation directions of electric field, and the solid dots indicate the propagation, the oscillation directions of magnetic field in and out of the page. So this is the directions of the wave traveling. So when electromagnetic wave shine on the on the interface, we know that there's a reflection. So this is a reflected ray, and this is the refracted ray. What we found is that initially unpolarized light at certain angle, when the angle of incidence is at a certain angle, then that reflected ray is actually being polarized, meaning that the intensity will cut by half. Okay, and so so this will happen. Let's say when on a sunny day, when you go on fishing, and if you if the at certain angle of incidence, what you see here, this is your eye. What you see here is that reflected ray is actually has a lower intensity, and that is because this reflected ray has been half of the intensity is being eliminated by the lake. Okay, you will see a lot of shimmering because the light is being polarized. Okay, so the reflected ray will be polarized if the angle of incidence is what we call the theta b here, and the refracted ray does not still is unpolarized. Okay, and we found out the the angle of refraction and the angle of incidence, they actually also obey certain there's certain relationship between them. So at what angle? This angle is called the Brewster's angle. When theta b and theta r, when they add up to 90 degrees, meaning that they are the reflected ray and refracted ray are perpendicular to each other, then the reflected ray will be polarized. Okay, so when theta r plus theta b that's equal to 90 degrees, then this ray is polarized, and so we know that that is the condition for that to happen. And from Snell's law, we know that n1. So this is my n1, and this is my n2. So n1 times sine theta b, that's equal to n2 sine theta r. Okay, Snell's law still applies, and we can see, and then we're going to utilize this relationship. So you have the n1 sine theta b that's equal to n2 sine. Your theta r is 90 minus theta b. So what is sine of this one? This will give you cosine theta b. So n1 sine theta b is equal to n2 cosine theta b. So when you rearrange this, you'll find that your theta b, so your theta b is inverse tangent of n2 over n1. Okay. So how do we find the Brewster's angle? The Brewster's angle can be found. Use the inverse tangent, and then your n2 over n1. N1 is where the light source is at, is where the Brewster angle is associated with. Okay, so it's actually the second material, the ratio of second index of refraction of the second material to the first material. And when the theta b is can be found by this, then when the angle of incidence is equal to theta b, then we know that reflected ray is polarized. This one remain unpolarized. Okay. So that's basically, so there are several interesting phenomena of electromagnetic wave. First of all, light can be polarized, and then light can be dispersed, and light follows the low reflection, low refraction, and light can be polarized if the angle of incidence is equal to the Brewster's angle, which can be found this. And light can also, light is also subject to total internal reflection. When the light source is in the material that has a higher index of refraction, then it can be polarized, so long as the angle of incidence is greater than the critical angle. Okay, so that concludes. Let me see. So that concludes the this chapter. Okay.